This is lesson 17 of the Quantum Mechanics, a mini lecture series titled Issues with Bohr's Model. Now, Bohr's model was great in the sense that it could explain hydrogen, the spectrum of hydrogen, very accurately. And he also managed to derive Balmer's formula using his new atomic model. Okay, and he could now use the Balmer formula to also determine the frequency of light given off by electrons as they transition between energy states. And so now there was a physical underlying theory for the emission spectra of elements, okay? It's that electrons jump up and down between energy levels and they give off light according to what's seen in the lab. However, there were some issues with the model. Okay? Issue number one, it only worked for hydrogen. It didn't work for multi-electron atoms like helium, the next simplest element, or lithium, etc., etc. It only worked for hydrogen. Number two, it couldn't explain, it couldn't account for the Zeeman effect. I'm going to explain what this is. Zeeman effect, so you simply take the same setup, okay, the emission spectra setup. You've got a hot gas, pass it through a prism, and it disperses the light. Place it in a magnetic field. So let's suppose you've got two spectral lines here. If you place the spectrum in a magnetic field, you will see splitting of the lines into more lines. Okay, so magnetic field on, magnetic field off. Now, if that's issue number two. Issue number three, if electrons are stable in their shells, then technically there should be no photons. No light should be emitted. Okay, if they're stable. That was another issue. And I'll explain the Zeeman effect a bit more. And so it was the Dutchman, Petier. Once again, I cannot pronounce these names. Apologies. Petier Zeeman, 1894. Okay, he showed that when spectral lines were placed in a magnetic field, they split into more lines. Okay, and eventually this led to more questions. Okay, what was really going on here? Why was there more splitting? An answer came from the German theoretical physicist Arnold Sommerfeld, who proposed that electrons orbit in elliptical orbits around the nucleus rather than circular orbits, as proposed by Bohr. And so you get orbits of different shape. And the shape of orbit, he gave it the symbol K. Okay, so Bohr used N to indicate size of the orbit. Okay, the bigger the orbit, the further away it is from the nucleus. Now, Sommerfeld introduced this, they're called quantum numbers. These two, N and K, called quantum numbers. Quantum because they've got to do with the atom, okay, with the quantum world, the world of the very small. Quantum numbers. And K can only take on values ranging from 0 to n minus 1. Okay. So for example, K equals 0 indicates a spherically symmetric orbit. Okay, sphere. That's also called an s orbital in atomic physics, just an FYI for those who actually have a bit more advanced knowledge in physics or even chemistry. K equals 1, the orbit becomes slightly elongated, That's called a p orbital. K equals 2, you get a more complex orbital, which I'm not going to draw. It's called a d orbital, and so on and so forth. So you get these different shapes. And the higher the value of K, the more the orbit becomes more intricate and complex. And also the directions of the orbit are quantized too. So you need another quantum number called the magnetic quantum number. Given the symbol m, lowercase m. Okay, so let's suppose you've got m equals, I'm just going to sketch these quickly. So when a magnetic field is applied, the electron can select from more orbits pointing in different directions, okay, with respect to the field. Okay, they've got different energies. If you look here at m equals 0 implies that the field is facing one direction. M equals 1, it's in different directions. So these are just sort of arbitrary directions. Drawn a graph here showing you the different directions. And so each energy state could now be assigned a set of 3 quantum numbers, n, k, and m.